In this video, we're going to briefly talk about how to determine the joint CDF of jointly continuous random variables x and y based on the joint PDF function. So the notation that we're going to use for the joint CDF is capital F of x, y, where the capital X and capital Y are the two random variables that we're finding the CDF for, and lowercase x and lowercase y are the values for x and y respectively that we're evaluating the CDF for. So we have this notation, which is equivalent to the probability that the random variable x is less than or equal to the lowercase value of x, while simultaneously y is also less than or equal to lowercase y. And the way that we compute that probability from the joint PDF is by integrating the joint PDF with respect to t in this function from negative infinity up to y. And after we do that, we also integrate s with respect to negative infinity up to x. And I should note that this form or this representation of the formula for computing the joint CDF is a little more complex than it looks like on the surface here, because it's possible that x and y are dependent random variables. So for example, we might have the constraint that y has to be less than or equal to x, in which case this integral right here might actually go only to the upper bound of x or something like that. So there can be some additional complexity that's kind of subtle and hidden in this formula, but this is the general formula that we use to find the joint CDF. And if we have indicator variables in our joint PDF, then those might change how we evaluate the integrals, etc. Conversely, once we have our joint CDF, we can obtain the joint PDF of jointly continuous random variables by taking the partial derivatives of the CDF with respect to x and with respect to y, respectively. So let's do an example of this. This is example 3.12 in the book. We're going to determine the CDF of the following jointly continuous PDF. And so we have our joint PDF notation here, and it looks like it's just the indicator variables from 0 to 1 for x and 0 to 1 for y, which really means that this is a uniform PDF where x and y form the unit square, and then it's 0 anywhere outside of out of that range. So we're actually going to jump over to Microsoft Word, where I have performed the details of this integration. And so let's scroll up here. And really the way you want to do this CDF is you want to consider cases for all possible combinations of x and y. And the first case we're going to consider is when both x and y are between 0 and 1. So if x and y are between 0 and 1, then we integrate these indicator functions from t ranging from negative infinity up to y, and x, or I should say this really should be an s right here, and s from negative infinity up to x. And because the inner integral does not depend on s, we can factor that out of the inner integral. And we can also use this indicator function right here to simplify the limits of integration for the inner integral, right? Because if it's 0 outside of 0, 1, then we don't need to integrate from negative infinity up to y. We can integrate 1 from 0 up to y. And so basically we use this indicator function to simplify this inner integral. And so now for this inner integral, we simply need to integrate 1 from 0 up to y with respect to t. And so when we do that, the antiderivative is t, evaluated from 0 up to y, which of course simplifies to y. And so this integral simplifies, the inner integral simplifies the entire expression to this right here. And because the inner integral is with respect to s, actually, so I'm using bad notation here, so I'll correct that on the fly. So because this inner integral does not depend on y, we can actually factor that y out of the remaining integral. And so that remaining integral is integrated from negative infinity up to x, the indicator function from 0 to 1 of s with respect to s. And because of this indicator function, we can rewrite this integral. Once again, I'm messing this all up. We can rewrite this inner integral, or this remaining integral, instead of having it run from negative infinity up to x, because we know that s has to be between 0 and 1, we can rewrite the lower limit as running from 0 up to x, because otherwise it's 0. The PDF is going to evaluate to 0, which means the integral would be 0. So we only care about the integral between 0 and x, and so we integrate 1 from 0 to x with respect to s, and similar to before, this is just going to simplify to x. And so our final result is xy for the case that x and y are between 0 and 1. So you might be tempted to be done, but if you think about it, this doesn't work for all the possible values of x and y. What if x was equal to -1? Or what if y was equal to 3? Then we might get a number that's not between 0 and 1, which we know is not possible for a probability. So this is a CDF, and the CDF is a probability. So the final value we get when we evaluate the CDF has to be between 0 and 1. So the CDF is only equal to xy when both x and y are between 0 and 1. So now we'll consider a different case, and I'll show you kind of how things simplify. Okay, for the second case, we have x being between 0 and 1, and y being greater than 1. And so we start to evaluate our joint CDF in the same way as before. We integrate the joint PDF with respect to t and s, where t runs from -infinity up to y, and s runs from -infinity up to x. However, because we know that y is greater than 1, and t is going to be, the indicator function will be 0 anytime t is not between 0 and 1, our inner integral, instead of running from -infinity up to y, can simplify to the integral from 0 up to 1 of 1, because we factored out the other indicator function of the inner integral, because it does not depend on t, and so it can come outside of this inner integral. And so we have the inner integral is the integral from 1, the integral of 1 from 0 up to 1 with respect to t. And so we evaluate the integral, and the antiderivative is y. Actually, the antiderivative is going to be t, evaluated at 0 up to 1, and so that's going to just simplify to 1. And so the entire expression is going to become the integral from -infinity up to x of the remaining indicator function with respect to s. And just like before, we can simplify this integral. So x is between 0 and 1, but -infinity is less than 0, and so our indicator function will evaluate to 0 anywhere outside that range. So our integral can be rewritten as the integral of 1 from 0 up to x ds, which ends up being the antiderivative is s, evaluated at 0 up to x, which simplifies to x. Okay, so in the second case, when x is between 0 and 1 and y is greater than y is greater than 1, then the joint CDF ends up being x for those values of x and y. There are three other cases that I want to talk about. So when x is greater than 1, but y is between 0 and 1, going through a similar process, we're going to get that the CDF, the joint CDF, is going to equal y in that case. If both x and y are greater than 1, then our CDF is going to simplify to 1. And then finally, if both x and y are less than 0, then our CDF is going to end up being 0 for those values of x and y. And so we actually have 5 different cases that we had to consider, and I showed you the second example in particular because the other examples sort of build off of that. And hopefully you can see exactly where these conclusions are drawn from. So for example, when both x and y are greater than 1, then both of our integrals are going to go from 0 up to 1, for example, and we're going to integrate 1 from 0 to 1 in both cases, and so we'll end up getting a 1 for our joint CDF. So when we put everything together, we get that the joint CDF of x and y is going to be this kind of complex, formulation of indicator functions and values of x and y. And so, for example, when x is between 0 and 1, but y is greater than 1, we just get the value x. When y is between 0 and 1, but x is greater than 1, then the CDF equals y. When both x and y are between 0 and 1, then we get xy. And when both x and y are greater than 1, then we get 1. Okay, and anything else is a 0, which is the case when x is less than 0 or y is less than 0. So that is our joint CDF. I also want to take this opportunity to find the If we had the joint CDF, how would we use that to find the joint PDF? And so I'm going to kind of simplify it for us. But basically, if we have this joint CDF right here, to find the joint PDF, we want to take the partial derivative of that with respect to x and also with respect to y. And what's going to end up happening here is that since we have to take the derivative with respect to both x and y, any of these terms here that don't include x and y outside of the indicators. So the indicators are important for knowing the limits of this. We don't actually take the derivatives of the indicators. So don't worry about those. Just because you have an indicator doesn't mean that we directly take the derivative of it. It's only going to matter if there's a function of x or a function of y outside of that. So for example, here we have a function of x, but not a function of y. So if we take the derivative of this with respect to x and y, when we take the derivative with respect to y, it's when we simplify to 0. Similarly, when we take the derivative of this with respect to x and y, when we take the derivative with respect to y, it's going to simplify to 1. But then when we take the derivative with respect to x, it simplifies to 0. And so that's going to happen for all of these except for this term right here. This highlighted too much. There's only this first term, right? This term right here that we care about. That's the only one where if we take the derivative with respect to x and y, it's not going to simplify to 0. So our partial derivatives of the CDF with respect to x and y will ultimately simplify to the partial derivative of this part of the CDF, the part that I highlighted previously here, with respect to x and y. Okay, and we take the derivative of that with respect to x, then this part just becomes 1, and so it simplifies to y, and we're still letting our indicators follow through here, so they're along for the ride, but we don't actually take the derivative of them in our derivative. And so now we have the partial of this with respect to y, and so the derivative of y with respect to y is just going to be 1. And so in the end, the joint PDF is going to simplify to the product of the indicator for x and y, where both have to be between 0 and 1, which is what we started with.